That is recording. Okay, so acid-base titrations. Just before the break, we learned all of the important information about acids and bases. Remember, acids, they produce the H pluses, right? So we produce H plus. And bases produce OHs, all right? And we talked about calculations involving H pluses in acids. If we wanted to calculate the pH, negative log of the H plus, right? And we could also then work the other way around. If we wanted to get the H plus back, we used that second function button and we did 10 to the negative pH, all right? So we talked about how we quantify acids and bases. And we didn't talk a lot about the chemical reactions, except for how to make acids and bases. Remember, we did a little lab just before the break on how to make acids and bases. And when we took something that was metal and we burnt it like magnesium, and we did you guys have a lab report that was due? Did I mark that lab report already? I can't remember. Now I'm just thinking there should have been a lab. Oh, that was quite earlier on. I did get yours marked. It was the 3U that I finished marking. So let's say I had something like magnesium and I burnt it. Remember, we burnt it in there, made a bright light, and we dissolved it in the water. We ended up with a base. So when metals react, we end up with a base. And when non-metals react, things like carbon and sulfur, and we put it in the water, we get an acid. Now, acid-base titrations has to do with a particular reaction that acids and bases can undergo, and that is a neutralization reaction. And I don't think that that's groundbreaking information for you, even though I haven't done the lesson on reactions of acids and bases. I think you all know that if I have an acid and I react it with a base, that they can neutralize each other, okay? They can react with each other and they can kind of cancel out their acidic and basic properties. Now, a titration is a special technique using all of this equipment that we have here that you'll be doing tomorrow, and it's a technique that allows us to react an acid with a base such that one of them we don't know the concentration of. So in this case, my hydrochloric acid, even though it says 0.5 up here, ignore it. Pretend we don't know what the concentration of this is, but for my base, 0.50 molar, we do know the concentration of this. By reacting the acid with the base together in this equipment in a very specialized controlled reaction, we should be able to take our known concentration to figure out the unknown concentration. That's what a titration does. It takes the concentration of a solution that we know, we do a reaction and we get some numbers, and it allows us to figure out the concentration of the unknown, all right? In this case, I know the base and I don't know the acid, but it could be the other way around. I could not know what the acid is, or sorry, I could know what the acid is and then figure out what the base is if I didn't know it. It doesn't make any difference. The key is that we're going to be able to calculate what the concentration is of a solution we don't know. Now, unfortunately, there is about 3 slides of just kind of explaining what this is. And so we'll write it all down, and after each slide, I'll explain to you what it means. And then we'll do a couple of examples of how we calculate it, and then I will show you how to do a titration, because tomorrow's lab, you will be doing this particular reaction. So notice there it says titration is a very accurate and precise technique used to determine the concentration of a substance in a solution. Today's titration is going to be using acids and bases, but you can use other types of chemical reactions to do titrations with. In university, we were doing a reaction called a redox reaction, which involves a completely different reaction, but one of the chemicals was purple, and when it reacted with the other thing, the purple disappeared, and when you were supposed to stop reacting, the purple would come back. And so a color change told us when to stop reacting. That's the key to a titration. When we do our titration, we're going to use an indicator that's going to change a color. And when the color change takes place, it means stop adding, stop reacting, and then we can get our numbers. So we're going to start with a standard solution. That's one that we know the concentration of. In this case, we're going to assume that we know the concentration of the base, 0.50 moles per liter. And from that known substance, we can eventually get what the concentration of the unknown substance is. And we're going to be using stoichiometry. We're going to be using our mole ratio. We're going to use our calculations that we already know how to do. So really, I'm not really teaching you anything new. We're going to be using all of the equations we already know how to use. We're just going to apply it to this laboratory technique. Let me know whether you got it. You done? You okay? So you're going to label this, but let me show you how to draw this without having to draw that fancy thing. So you can see here I've got a tall kind of cylinder, and I actually have it upside down because that's the way you store it when you're not using it. So this tall thing is called a buret, and all I need you to do, draw a couple of parallel lines, put a circle with an X in it, and then put a little tip on the end, and you can then label the buret and the stopcock, and then underneath there, we're going to use an Erlenmeyer flask to do our reacting in. We were just changing the colors. We weren't accurately measuring. It's the same idea that we're adding acid and base to change the colors. This becomes a titration because we're doing accurate measurements of volumes, right? So again, we're doing the same thing. Then we're going to stop at a certain color. But the accurate measurement is what makes it a titration. Because then we can do the math to figure out the concentration. So three main pieces of equipment: a buret, a very accurate graduated cylinder. You've seen those graduated cylinders before. They're tall, they've got lots of markings on them. This thing is very tall and very skinny, and it has many, many, many markings on it. I don't know if you can see the markings on the little buret that's up here in the picture, but it goes 10, 20, 30, 40, 50. That's the same as ours. And in this case, you can also see that the divisions, there's 10 little divisions in between each. Actually, this goes up by one milliliter. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. But on this particular one, each milliliter is also divided into 10. So if I were to look at it on here, and again, you don't have to write this, but let's say we had one of the milliliters in here. This is the 5 milliliter mark, right? And there's the 6 milliliter mark. You know, if you could imagine then that we've zoomed in on this, and there's 5 and there's 6, then this would also still go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you'd have there 5 milliliters. This one here would be 5.5 milliliters, and this one here would be 6.0 milliliters. So you can see on this one, there's many little divisions. We can measure it down to the 10th of a milliliter. We can even do better than that. If the bottom of the meniscus, when we measure, if the bottom of the meniscus ends up halfway between a mark, like in here, all right, halfway between, that'd be 5.5, 5.6, 5.7. Halfway between 5.7 would be 5.75 milliliters. We can always measure with a burette to 2 decimal places. 2 decimal places. That's what makes a burette so accurate at measuring volumes, that it's got so many little marks on it that we can get a volume to 2 decimal places. That's an incredible tiny amount of volume. That's what makes it so accurate, okay? It contains the titrant, the stuff that we're going to titrate. In this case, we're going to put the base. In here, it's usually the one we know the concentration of. So we're going to put that in there. The way we control the liquid coming out of the burette is a little tap here. Its technical term is called a stopcock. So if you need to giggle, you can. Anybody need to giggle? No, I'm the only juvenile in the room here. I guess I am, okay. It's like a little tap, and when you've got the tap parallel, the liquid comes out, and when you've got the little tap perpendicular, it stops it, okay? And we let that liquid go into an Erlenmeyer flask. This is where we usually put the thing we want to find the information about. We're going to put some in there, and we mix it up. I don't have it in a good position. And we put it in there, and we swirl it, and we mix it. And in the end, our indicator will tell us when it's neutralized. That's going to tell us stop mixing, okay? All right. And when you read the volumes, you should always put your eye in line with the meniscus. And here I've got, you know, on my little picture I found online, there's a little eye, and you can see that eye lining up with the meniscus there. And so, you know, you don't have to actually put your eye that close. That's just a little representation. And in actual fact, that little eye is an animated eye. Take a look at it when I switch slides. I don't know whether we'll see it. Did you see what the eye did? Did you see it? Did you see it blink? Isn't that fun? It just blinks. It's just, you know, that's just fun. Can I do it again? I'll go back. It blinks when I come onto the screen. Blink. Did you see it blink? All right, that's fun. Okay, you can write that down as well. That's the last bit of information on how the neutralization is used to find out the concentration. So in an acid-base titration, an acid is titrated with a base until they have neutralized perfectly. Okay. At this point, the moles of acid equals the moles of base, and we call it the neutralization point. It's where neutralization has taken place. The way we're going to know whether neutralization takes place or not is using an indicator. And we already have seen the color changes involved in an indicator, right? Mark reminded me when we had the giant test tube there. Remember that? We had the universal indicator in there. This is just one indicator, which means it's only going to change once. And it's only going to change when we've neutralized the solutions. So let me just show you what that's going to look like. Now, getting set for my titration, I've got a bunch of beakers here, and you're going to have the same thing. This one here I've already labeled with a Sharpie marker. I've labeled it water, so I'm going to put a little more water into that. This one here has an A on it. It's labeled with an A to represent the acid, and I've already put some of the acid in it. And this other one here is labeled B for base. And I'm gonna use this base in a moment to prepare the Buret. But I'm getting ahead of myself a little bit because I want to show you what the color change looks like. Now, this is not a titration because all I'm doing is adding a little bit of acid to base, and we're not measuring it. A titration, we have to measure it. But just to give you a little demonstration, I'll take a little bit of the acid, and I'm not going to take much, just a little splash. And I'm going to add some water to it just so that we can see the color change a little better. And I'm going to add some phenolphthalein to this. Now, phenolphthalein in acid is colorless. And you can see there, it's colorless. And now I'm going to slowly add a little bit of base. And if I add just a tiny bit of base, let's see if I've added too much, you'll notice the color disappeared. There was more acid than base. I didn't successfully neutralize it all. So if I add a little bit more, I may get to the point where the color doesn't disappear and the color stays. Add a little bit more, and there you can see the color stays. It means I've neutralized the acid, but in actual fact, I've probably added too much base. Now this isn't a titration. Oh, is it going away slowly? That's not bad. That's close. That's close to being neutralized. Oh, it disappeared, which means it slowly did neutralize it. The next little bit more should keep it nice and purple, I would hope. So the reason this isn't a titration is because we didn't measure the volume. When we do a titration, we want to measure very carefully how much we added. So that's what we're looking for, but we want to do it while we measure, and we don't want to send it too pink. We want it to just be a little hint of pink because we want to just get to the neutralization point. I probably went past the neutralization point, and this would be, basic. It would have a high pH. All right. So let's first do a couple of practice problems before I actually do a titration. So we'll do two examples, and then I'll do an actual titration with you. Okay, so in this question, you can see here we've got 23.45 milliliters of 0.275 moles per liter sodium hydroxide. So just like in our scenario, we know what the concentration of the base is. And we've titrated it. We reacted it. That was added to 10 milliliters of sulfuric acid. Here is our balanced chemical equation. Now let me give you a little brief explanation on what took place. This is a pipette. We've used the pipettes already, right? Remember when we made our or did we make, no, we didn't make solutions using the liquids because we had a weather day in there. I would have shown you how to use a pipette. This device draws up exactly 10 milliliters. So that would have been used to measure the sulfuric acid and to put the sulfuric acid into the Erlenmeyer flask. Then we would have used the Buret to open that up and mix it until 23.45 milliliters caused the color change to stay. And then we stopped. That told us that we had neutralized the acid that we had in the bottom. So now we're going to get ready to calculate. Notice that we've got concentrations in moles per, oh, why isn't my pen writing on the screen? I'm very concerned. Let's go back and let's take this out of here. So notice that we have moles per liter. So we're going to be using our equation, molarity, capital M, equals moles over liters. And I'm just going to put that off to the side. Remember, we can make our triangle out of that. Moles on the top, molarity, and liters on the bottom, right? Remember how we do our triangle? Maybe we'll put that one up in the corner over here, right? So remember, we've got moles and then capital M for molarity and liters as the concentration. Let's write our information down like we do when we do a stoichiometry problem. 23.45 milliliters of sodium hydroxide. 23.45 milliliters. But remember, we like it in liters. So how many steps do I move that in order to get it to liters? Yep. 3. So 1, 2, 3, 0.0234 liters. And for the acid, 10 milliliters or 0.0100 liters. Okay? And we make our little map, right? Moles, moles. And we know the concentration of the sodium hydroxide, 0.275 capital M, molar. Okay? That's our concentration. Now, the question asks, what's the concentration of sulfuric acid? In other words, what's the molarity? Capital M. Once we figure out, all right, what that moles is, we can put it into the moles. Here we know the liters, we can put it into the liters. So over here in this space right here, taking this information here and here, we can find the molarity because that's going to be equal to moles divided by liters. Okay? I believe we put an X in there, but I'll deal with that in a moment. So let's start the problem. We want to find moles. I have liters and molarity. What's my equation going to be? Yep. M times L. So moles equals M times L. 0.275 times 0.0345 liters. And now we need calculators. Yep, what do you got? going to be a tiny number. Okay? 6.45 times 10 to the negative 3 is good. Yeah, 645 moles. Either or, I don't care. If you've got your calculator set for scientific notation, then just giving it to you in scientific notation. I don't care which way. Now, if you remember our steps, we now need to use the mole ratio, right? And remember, I think we had an X in this position because that's what we were trying to find. Remember how we used to do that? So we've got X over the moles, there it is there, 0.00645 equals, right? So X over that number is equal to 1 over 2. 1 over 2. Does that look familiar? Right? Again, what did we do? X over the moles, which we got from down below, is equal to 1 over 2. And then I bring that up to the other side, right? Remember how we do that? The opposite operation? X is going to be equal to 0.00645 divided by 2. And, yep. 0.003225. And again, that's a moles. The unit is moles. Okay, I'm going to put some more squiggly lines around this. Sorry for the big mess, but that's what I'm going to do. I'm going to isolate those things. Now we're into our last step. We want to find the concentration. We know how much acid we used, and we know the moles, so we can put it into that equation. The moles come from down there, 0.003225 over 0.01000. I got an extra 0 on there and didn't need it. And what do we get? Yeah, Conrad? 3.2, and I'm going to round it to 323 molar because I want it to look the same as the one that we started with. Notice how it only has 3 digits or three decimals there, so I want it to look the same. Excellent. That is correct. That is our final answer. So what did we do? We took a solution where we knew what the concentration was. We knew how much it took to neutralize it. We did a little calculation using the moles and the mole ratio. Then we put it into the concentration calculation, and we found a new concentration. Okay, and that's what stoichiometry is. It's the same type calculations that we did before when we did stoichiometry, except now we're finding the concentration of the unknown one. We will do one more, and then I'm going to show you an actual titration. So again, we need to find the concentration. That's the molar concentration. So we need our triangle that we just used. Molarity, capital M, is equal to moles per liter. But notice here that we've got grams. That means we're going to have to use our molar mass calculation. Remember the equation, molar mass is equal to grams over moles. So its triangle, and again, what goes on the top? Grams, good. I want you guys to be able to make your own triangles. Grams, molar mass, moles. We're going to need that as well this time. Just like before, write everything that you need underneath. 17.05 milliliters, which I would turn right away 3 steps to 0.1705 liters. In this case, we have 10 grams. And it asks, what is the concentration of the barium hydroxide? So in this case over here, we're going to need our molarity is equal to moles per liter. So it's this side that we need the moles per liter this time. We're going to go down to moles and over to moles. Again, X. If I have grams of HNO3, then I'm going to need to find moles. In this case, moles is equal to grams over molar mass. Do we remember how to find a molar mass? What do I need to do? Been a long time. All the arrows, correct, the arrows. So I need HNO3. Anybody remember the numbers without looking at the periodic table? Yeah? Ooh. 16.0 times 3. What's, ooh, 14, impressive. Oops, times 1 and 1 times 1. That's what he did over the break. Isaac memorized the periodic table. That's good, that's fun. Oh, yes. What, she memorized the names?
But then they asked her about them, and then she would explain them.
Oh. Again, that just means she's got really pushy, geeky parents. Who's kidding who? I may be geeky, but I'm not pushy. I don't think. What do we have? Tell me a number. Tell me. 63. 63.0 grams per mole. Okay, again, that's where the unit comes from. So now we can find the moles. I have 10 grams divided by 63.0 grams per mole. And so how many moles of that do we have? Yep? 158 is good. Moles. So, again, we need our mole ratio. Mole ratio. I'm going to put a squiggly line around that so I don't get it mixed up. So again, X over whatever I'm starting with, 0.158. X over that, and I'm going to it, is 1 over 2 again, right? X over the moles is 1 over 2. X is equal to 0.158 divided by 2. And I am not leaving myself a lot of room to finish this calculation on the slide. But anyway, we'll get her in. Oh, I wanted to move this thing. Move you. Nice. And what do we have? 0.079 moles. I now know the moles, and I know the liters. And I can get the concentration. I'll put squiggly line in there again. Molarity is equal to the moles, 0.079 moles divided by 0.01705 liters, and I apologize for those watching the video that this is a mess. And what do we got? So the moles, right, on the top, the liters that we used there on the bottom. Yep. 4.6, is it that high? 4.6, was there, you got one more digit? 6.3? Capital M, 4.63 molar. That's a really high molarity. We must have just made those numbers up, but that's okay. That gets the idea across. Sorry? Because it was so high? Yeah, we must have just made that question up, but that's okay. The calculation is the important part. Okay, I'm actually going to stop the video at this point, and then I'll do the demonstration, because for me to just do the demonstration and be talking into the video doesn't make a whole lot of sense. Let's switch that to there. The heat on.